What if the universe held secrets so strange, so extreme, that they defy everything we think we know about reality? Picture this: a star, millions of times more massive than our Sun, collapses in a fiery explosion. But instead of vanishing into darkness, it leaves behind something even more bizarre: a cosmic enigma so dense, a single teaspoon of it would weigh billions of tons. This is the world of neutron stars and pulsars, some of the most mysterious and mind-bending objects in the universe. From their birth in the ashes of supernova to their bizarre behaviors that baffle even the brightest scientists, these stellar remnants are packed with mysteries that challenge our understanding of physics itself. In this video, we're diving deep into the 25 greatest mysteries of neutron stars and pulsars phenomena that push the boundaries of what we thought was possible. So buckle up, because by the end of this journey, you'll see the universe in a whole new light, ready to uncover the secrets of these cosmic oddities. Let's begin. Now, let's step into the fiery chaos of a star's final moments. Imagine a star far more massive than our Sun, reaching the end of its life. It doesn't go quietly. Instead, it explodes in a cataclysmic event known as a supernova, one of the most violent and energetic phenomena in the universe. But this explosion isn't just an end, it's also a beginning. From the ashes of this cosmic inferno, something extraordinary is born: a neutron star. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity. The outer layers are blasted away in the supernova, but the core is crushed into an unimaginably dense object. We're talking about a sphere roughly the size of a city, yet packing the mass of 1.4 times that of our Sun. To put it another way, if you could scoop up a teaspoon of this material, it would weigh billions of tons. That's the kind of density we're dealing with here. But how does this happen? During the collapse, protons and electrons are forced together, merging to form neutrons. This creates a neutron-rich core so dense that it defies our everyday understanding of matter. The physics at play here is so extreme that scientists are still trying to fully grasp it. For instance, what happens to matter under such crushing pressure? Does it break down into even smaller particles like quarks, or does it remain in this bizarre neutron state? These are questions that keep researchers up at night. What's even more fascinating is that not all massive stars become neutron stars. If the star is too massive, it collapses further, forming a black hole. But if it's just the right size, a neutron star is born. This delicate balance between creation and destruction is one of the many reasons why the birth of neutron stars remains one of the greatest mysteries in astrophysics. So as we peel back the layers of this cosmic enigma, we're left with more questions than answers. What exactly happens inside a collapsing star? How does matter behave under such extreme conditions? And what secrets do these neutron stars hold about the fundamental laws of the universe? These are the mysteries we'll continue to explore as we journey deeper into the strange world of neutron stars and pulsars. Now, let's take a closer look at one of the most jaw-dropping aspects of neutron stars: their mind-bending density. Picture this: a single teaspoon of material from a neutron star would weigh billions of tons. That's not a typo, billions. To put it in perspective, that's like squeezing the entire mass of Mount Everest into a tiny spoon. It's a density so extreme that it challenges everything we know about the nature of matter. But how does matter even get this dense? When a massive star collapses, its core is compressed to such an extreme degree that atoms can no longer exist in their normal form. Protons and electrons are forced together, merging into neutrons, and the result is a neutron-rich material so tightly packed that it defies imagination. The gravitational pull is so intense that it crushes matter into a state that scientists are still struggling to fully understand. Here's where things get even more puzzling. Under such extreme pressure, the rules of physics as we know them start to break down. For instance, what happens to the neutrons themselves? Do they remain intact, or do they break apart into even smaller particles like quarks? Some theories suggest that the core of a neutron star might contain a strange form of matter called quark-gluon plasma, a state that hasn't been observed anywhere else in the universe. And then there's the question of how matter behaves under these conditions. On Earth, we're used to solids, liquids, and gases, but inside a neutron star, matter exists in a state that's unlike anything we've ever encountered. It's so dense that it's often described as a nuclear pasta, with layers of material arranged in shapes resembling spaghetti or lasagna. Yes, you heard that right, cosmic pasta. This density paradox isn't just a curiosity, it's a window into the fundamental laws of the universe. By studying neutron stars, scientists hope to unlock secrets about how matter behaves under the most extreme conditions imaginable. But for now, the physics of these ultra-dense objects remains one of the greatest unsolved mysteries in astrophysics. As we move forward, we'll dive into another fascinating aspect of neutron stars, the mysterious beams of radiation they emit, known as pulsar beams. What causes these beams, and why do they pulse with such precision? Stay tuned as we unravel this cosmic phenomenon next. Now, let's shift our focus to one of the most mesmerizing features of neutron stars, their pulsar beams. Imagine a lighthouse in space, but instead of light, it's emitting intense beams of radiation that sweep across the cosmos. These beams are what give pulsars their name, short for pulsating stars. But how do these beams form, and why do they pulse with such incredible precision? When a neutron star spins, its incredibly strong magnetic field channels charged particles along its magnetic poles. These particles accelerate to nearly the speed of light, releasing beams of radiation in the process. Because the magnetic poles aren't aligned with the star's rotational axis, these beams sweep through space like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect it as a pulse of radiation, hence the name pulsar. What's truly astonishing is the regularity of these pulses. Some pulsars spin hundreds of times per second, and their pulses are so precise that they rival the accuracy of atomic clocks. This precision has made pulsars invaluable tools for astronomers, helping them test theories of gravity and even navigate spacecraft. But here's where the mystery deepens. While we understand the basic mechanics of pulsar beams, the exact details of how they form and why they're so focused remain hotly debated. For instance, how do the charged particles accelerate to such extreme speeds? And what keeps the beams so tightly collimated, even over vast distances? Some theories suggest that the intense magnetic fields play a key role, while others propose that the extreme environment near the neutron star's surface creates unique conditions that we're only beginning to understand. Another puzzling aspect is the variety of pulsar beams we observe. Some pulsars emit radio waves, while others shine in X-rays or even gamma rays. Why do different pulsars emit different types of radiation? Is it due to differences in their magnetic fields, their spin rates, or something else entirely? These questions highlight just how much we still have to learn about these cosmic lighthouses. As we continue to study pulsar beams, they offer us not just a glimpse into the behavior of neutron stars, but also a chance to explore the limits of physics itself. What other secrets do these beams hold, and what can they teach us about the universe's most extreme environments? Next, we'll explore another intriguing mystery, the missing pulsar in Supernova 1987A. Why hasn't a pulsar been detected in one of the most famous supernova remnants in history? Stay tuned as we dive into this cosmic puzzle. Now, let's turn our attention to one of the most baffling cosmic mysteries, the missing pulsar in Supernova 1987A. This supernova, which exploded in the year 1987, was one of the brightest and most closely observed stellar explosions in history. It was so bright that it could be seen with the naked eye, even though it occurred in a neighboring galaxy, the Large Magellanic Cloud, over 160,000 light-years away. When a massive star explodes as a supernova, it often leaves behind a neutron star or a pulsar. But in the case of supernova 1987A, despite decades of searching, no pulsar has been detected. This absence has left astronomers scratching their heads. What happened to the neutron star that should have formed? One possibility is that the neutron star is simply hidden from view. The supernova remnant is filled with dense clouds of gas and dust, which could be blocking our view of the pulsar's beams. If the beams aren't pointing toward Earth, we wouldn't detect them, even if the pulsar is there. Another theory suggests that the neutron star might have formed but is spinning too slowly to produce detectable pulses. But there's a more dramatic possibility. The neutron star might have collapsed into a black hole. If the core of the star was particularly massive, it could have bypassed the neutron star stage entirely and formed a black hole instead. This would explain why no pulsar has been found, but it raises new questions about the conditions required for such an outcome. Some scientists have even proposed that the neutron star could be surrounded by a thick cocoon of material, preventing its radiation from escaping. This material might have been ejected during the supernova explosion, creating a shroud that hides the pulsar from our telescopes. The mystery of the missing pulsar in supernova 1987 reminds us that even the most studied cosmic events can hold surprises. It challenges our understanding of how neutron stars form and evolve, and it keeps astronomers searching for answers. Could the pulsar be there, hidden in the shadows, or has it vanished into a black hole, leaving behind only questions? As we continue to explore this enigma, it serves as a reminder of how much we still have to learn about the life cycles of stars and the remnants they leave behind. Next, we'll delve into another fascinating phenomenon, the glitch phenomenon, where pulsars suddenly speed up their rotation. What causes these strange hiccups in the heartbeat of the cosmos? Stay tuned as we uncover the secrets behind these cosmic glitches. Now, shifting our focus to another intriguing cosmic puzzle, let's explore the glitch phenomenon, a strange and sudden change in the behavior of pulsars. Imagine a cosmic clock ticking with incredible precision, only to suddenly speed up without warning. This is exactly what happens during a pulsar glitch, where these rapidly spinning neutron stars experience a sudden increase in their rotation speed. It's as if the universe itself has hit the fast-forward button, leaving scientists puzzled about what could cause such a dramatic shift. One of the leading theories to explain these glitches involves starquakes. Just like earthquakes on Earth, starquakes are massive shifts in the crust of a neutron star. These crusts are incredibly dense and rigid, but under extreme pressure, they can crack and rearrange themselves. When this happens, the star's rotation can suddenly speed up, creating the glitch we observe. Think of it like a spinning ice skater pulling their arms in closer to their body, causing them to spin faster. But starquakes aren't the only explanation. Another fascinating possibility lies deep within the neutron star itself. The interiors of these stars are thought to contain a superfluid, a state of matter that flows without friction. This superfluid can interact with the star's solid crust, transferring angular momentum and causing the crust to spin faster. It's like a hidden engine inside the star, occasionally revving up and altering its rotation. These glitches aren't just random cosmic quirks, they offer a rare glimpse into the inner workings of neutron stars. By studying them, scientists can learn more about the extreme conditions inside these objects, from the behavior of superfluid matter to the strength of their crusts. Each glitch is a clue, helping us piece together the complex physics that govern these mysterious remnants of stellar explosions. As we continue to unravel the secrets of pulsar glitches, one thing is clear. These cosmic hiccups are more than just anomalies. They're windows into the hidden dynamics of neutron stars. Next, we'll dive into the origins of magnetars, neutron stars with magnetic fields so powerful they defy imagination. What makes these cosmic powerhouses so unique? Stay with us as we uncover the mysteries of these magnetic giants. Now, let's turn our attention to one of the most extreme objects in the universe, magnetars. These are neutron stars, but with a twist. Their magnetic fields are so powerful they can distort the very fabric of space around them. To put it into perspective, a magnetar's magnetic field is 1,000 trillion times stronger than Earth. If a magnetar were located halfway between the Earth and the Moon, it could wipe the data from every credit card on our planet. That's the kind of cosmic power we're talking about. So, how do these magnetic monsters form? Like all neutron stars, magnetars are born from the explosive deaths of massive stars in supernova. But what sets them apart is the way their magnetic fields are amplified during their formation. When a massive star collapses, its core compresses into a neutron star, and in some cases, the star's magnetic field gets wound up and concentrated to unimaginable levels. This process is like taking a spinning top and twisting it tighter and tighter until it becomes a powerhouse of energy. But why are magnetars so much more magnetic than regular neutron stars? One theory suggests that it all comes down to the star's initial conditions. If the collapsing star was spinning extremely fast and had a strong magnetic field to begin with, the resulting neutron star could inherit and amplify those traits, turning it into a magnetar. Another possibility is that the turbulent motions of charged particles in the newborn neutron star's interior generate a dynamo effect, supercharging its magnetic field to extraordinary levels. Magnetars are also known for their dramatic outbursts. Occasionally, they release massive bursts of energy in the form of X-rays and gamma rays, lighting up the cosmos like a cosmic flare. These outbursts are thought to be caused by the immense stress on the star's crust, which can crack and release energy stored in its magnetic field. It's like a pressure cooker finally letting off steam, but on a cosmic scale. Studying magnetars gives us a unique opportunity to explore the limits of physics. Their extreme magnetic fields challenge our understanding of how matter behaves under such conditions, and their outbursts provide clues about the inner workings of neutron stars. As we continue to observe these magnetic giants, we're not just learning about them, we're uncovering the secrets of the universe itself. Next, we'll explore the mysterious connection between neutron stars and fast radio bursts, those fleeting cosmic signals that have puzzled astronomers for years. What could be causing these brief but powerful bursts of energy? Stay with us as we dive into this cosmic enigma. Now, let's shift our focus to one of the most puzzling phenomena in the cosmos, fast radio bursts, or FRB. These are incredibly brief but intense bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in an entire day. First detected in 2007, FRBs have since become a major area of study, with astronomers racing to uncover their origins. And here's where neutron stars and magnetars come into the picture. Could these extreme objects be the source of these mysterious signals? One leading theory suggests that magnetars, with their unimaginably strong magnetic fields, might be responsible for producing FRBs. Remember those dramatic outbursts we talked about earlier? Well, some scientists believe that the same processes that cause magnetars to release bursts of X-rays and gamma rays could also generate fast radio bursts. The idea is that the intense magnetic fields of magnetars could twist and snap, releasing enormous amounts of energy in the form of radio waves. It's like a cosmic whip cracking, sending shock waves across the universe. But magnetars aren't the only suspects. Some researchers think that collisions between neutron stars could also produce FRBs. When two neutron stars spiral toward each other and eventually merge, the resulting explosion is one of the most energetic events in the universe. This collision could create a shock wave that emits a burst of radio waves, explaining the fleeting but powerful signals we detect. It's a cosmic fireworks show, but one that happens in the blink of an eye. There's also the possibility that FRBs come from isolated neutron stars. These lone wanderers without companions or surrounding debris might occasionally release bursts of energy as they interact with their environment. For example, if a neutron star passes through a dense cloud of gas or dust, the interaction could trigger a fast radio burst. It's like a cosmic spark igniting briefly before fading away. Despite these theories, the true origin of FRBs remains a mystery. What makes them even more intriguing is that some FRBs repeat while others are one-time events. This has led scientists to wonder if there are multiple sources or mechanisms at play. Could some FRBs come from magnetars, while others are produced by neutron star collisions or even entirely different cosmic phenomena? The search for answers continues, with astronomers using advanced telescopes and detectors to capture and analyze these elusive signals. As we piece together the puzzle of fast radio bursts, we're not just uncovering the secrets of these mysterious signals, we're also learning more about neutron stars and the extreme conditions they create. Whether it's the magnetic fury of a magnetar or the explosive power of a neutron star collision, FRBs remind us just how dynamic and unpredictable the universe can be. Next, we'll explore another fascinating aspect of neutron stars' X-ray pulsars. What makes these objects emit X-rays instead of radio waves, and how do they fit into the larger picture of neutron star mysteries? Stay tuned as we dive deeper into the cosmos. Now, let's turn our attention to a different kind of cosmic beacon, X-ray pulsars. Unlike the radio waves we've been discussing, these neutron stars shine brightly in the X-ray part of the electromagnetic spectrum. But what makes them so special, and why do they emit X-rays instead of the familiar radio pulses? The answer lies in their unique environments and the way they interact with their surroundings. X-ray pulsars typically form in binary systems, where a neutron star orbits a companion star. This companion is often a massive star that's still burning fuel, or sometimes even a white dwarf. As the neutron star and its companion dance around each other, the intense gravitational pull of the neutron star can strip material away from the companion. This stolen gas doesn't just disappear, it spirals down onto the neutron star's surface, creating an accretion disk. It's this process of accretion that powers the X-ray emissions. As the material in the accretion disk falls toward the neutron star, it heats up to incredibly high temperatures, reaching millions of degrees. At these extreme temperatures, the material glows brightly in X-rays. When this hot gas finally reaches the neutron star's surface, it slams into the star's magnetic poles, releasing even more X-rays in focused beams. Because the neutron star is spinning, these beams sweep across space like a lighthouse, creating the pulsating effect we observe. But why do X-ray pulsars behave so differently from regular radio pulsars? The key difference lies in their energy source. Regular pulsars rely on their rapid rotation and strong magnetic fields to generate radio waves, while X-ray pulsars are powered by the accretion of material from their companion stars. This means that X-ray pulsars are often younger or more active than their radio-emitting counterparts, as they require a steady supply of material to keep shining. Interestingly, not all X-ray pulsars are the same. Some are transient, meaning they only emit X-rays sporadically, while others are persistent, shining steadily over long periods. This variability depends on factors like the amount of material being accreted and the strength of the neutron star's magnetic field. In some cases, the accretion process can even cause the neutron star to spin faster, a phenomenon known as spin-up. The study of X-ray pulsars has opened up new windows into the behavior of neutron stars and the extreme physics that govern them. By observing these objects, scientists can learn more about the processes of accretion, the properties of neutron star magnetic fields, and even the nature of the material being pulled from companion stars. Each X-ray pulsar is like a cosmic laboratory, offering clues about the universe's most extreme environments. As we continue to explore the mysteries of neutron stars, our next stop takes us to a particularly intriguing type of system, black widow pulsars. These cosmic predators are known for slowly destroying their companion stars. What makes them so deadly and how do they form? Let's find out as we journey further into the cosmos. Now let's venture into the eerie and fascinating world of black widow pulsars. These cosmic predators are named after the infamous spider, and for good reason. They're known for slowly consuming their companion stars, leaving behind only a trail of destruction. But how do these deadly systems form, and what makes them so lethal to their stellar partners? Black widow pulsars are a type of millisecond pulsar, meaning they spin incredibly fast, hundreds of times per second. What sets them apart is their relationship with their companion stars. Unlike the binary systems we've discussed earlier, where the neutron star and its companion coexist relatively peacefully, black widow pulsars are far more destructive. These systems begin much like other binary pairs, with a neutron star and a smaller companion star orbiting each other. However, over time, the neutron star's intense gravitational pull and powerful radiation begin to take a toll on its partner. The neutron star's radiation is so intense that it bombards the companion star, stripping away its outer layers. This process, known as ablation, slowly erodes the companion star, leaving it smaller and smaller over time. As the companion star loses mass, some of this material is funneled onto the neutron star, feeding its rapid rotation and making it spin even faster. This creates a vicious cycle. The more the neutron star spins, the more radiation it emits, and the more it damages its companion. But the destruction doesn't stop there. In some cases, the neutron star's radiation can completely evaporate the companion star, leaving behind only a faint remnant or even nothing at all. This is why black widow pulsars are often found in systems where the companion star is either extremely small or entirely absent. In fact, some black widow pulsars are so efficient at destroying their companions that they're left orbiting what's essentially a ghost, a faint, barely detectable trace of what was once a star. What makes black widow pulsars particularly intriguing is their role in the evolution of binary systems. They represent one of the final stages in the life of a neutron star binary, where the neutron star has effectively consumed its partner. Studying these systems helps scientists understand the ultimate fate of binary stars and the extreme processes that can occur in the universe. As we peel back the layers of this cosmic mystery, we're reminded of the sheer power and unpredictability of neutron stars. Black widow pulsars are a stark reminder that even in the vastness of space, destruction and creation often go hand in hand. And with that, we're ready to explore another enigmatic aspect of neutron stars, isolated neutron stars, which seem to exist without any companions at all. What secrets do these solitary objects hold? Let's find out. Now, let's turn our attention to a different kind of cosmic loner, isolated neutron stars. Unlike the black widow pulsars we just explored, these neutron stars seem to exist entirely on their own, with no companion stars or surrounding debris to keep them company. But how do these solitary objects come to be, and why are they so elusive? Isolated neutron stars are thought to form in one of two ways. The first possibility is that they were once part of a binary system, much like the black widow pulsars, but their companion star was completely destroyed or ejected during a violent event, such as a supernova explosion. In some cases, the force of the explosion can be so powerful that it sends the neutron star hurtling through space at incredible speeds, leaving it isolated and far from its original location. This process, known as a natal kick, can propel a neutron star across the galaxy, making it difficult to trace back to its origins. The second possibility is that these neutron stars were born alone from the collapse of a massive star that had no companion. While this scenario is less common, it's not impossible. In either case, isolated neutron stars are fascinating because they challenge our understanding of how neutron stars form and evolve. Without a companion to interact with, these stars are free to roam the galaxy, untethered and unseen. Detecting isolated neutron stars is no easy task. Unlike pulsars, which emit regular beams of radiation that make them easier to spot, isolated neutron stars often lack the same kind of detectable signals. Some of them, known as radio-quiet neutron stars, emit very little radio waves, making them nearly invisible to traditional radio telescopes. Others might emit X-rays or gamma rays, but these signals can be faint and easily overshadowed by other cosmic phenomena. One of the most intriguing aspects of isolated neutron stars is their potential to reveal secrets about the universe's most extreme environments. Because they're not influenced by nearby stars or debris, their properties such as their magnetic fields, temperatures, and rotation rates can provide a clearer picture of the conditions inside a neutron star. Studying these solitary objects could help scientists refine their models of neutron star interiors and better understand the exotic states of matter that exist within them. Despite their elusiveness, isolated neutron stars are a reminder that the universe is full of surprises. They challenge us to look beyond the obvious and explore the quieter, more hidden corners of space. And as we continue to search for these cosmic loners, we're reminded that even in the vastness of the universe, there's always more to discover. With that, let's move on to another mystery, neutron star collisions, where the universe's most extreme objects come together in spectacular fashion. What happens when two neutron stars collide? Let's find out. Now, let's shift our focus to one of the most dramatic events in the cosmos, neutron star collisions. Imagine two of the densest objects in the universe, each packing the mass of a star into a city-sized sphere, hurtling toward each other at unimaginable speeds. When they collide, the result is nothing short of spectacular, unleashing energy that ripples across the fabric of space-time and creates some of the universe's most precious elements. Neutron star collisions are incredibly rare, occurring only a handful of times in a galaxy over millions of years. But when they do happen, they leave behind a trail of cosmic clues that scientists are eager to decode. One of the most significant discoveries linked to these collisions is the detection of gravitational waves ripples in space-time predicted by Albert Einstein over 100 years ago. In 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves from a neutron star collision for the first time. This groundbreaking observation not only confirmed Einstein's theory, but also opened a new window into the universe. But the surprises don't end there. Neutron star collisions are also cosmic forges, producing heavy elements like gold, platinum, and uranium. These elements, which are essential to life as we know it, are created in the intense heat and pressure of the collision. During the event, neutron-rich material is ejected into space, where it undergoes a process called rapid neutron capture, or the R process. This process transforms ordinary matter into some of the heaviest elements in the periodic table, scattering them across the cosmos. In fact, much of the gold on Earth may have originated from ancient neutron star collisions. So, what exactly happens during a neutron star collision? As the two stars spiral closer together, their immense gravitational pull distorts space-time, sending out gravitational waves. When they finally collide, the impact generates a burst of gamma rays, followed by a glowing afterglow of light across multiple wavelengths. The collision can result in one of two outcomes: the formation of an even more massive neutron star or the birth of a black hole. The outcome depends on the combined mass of the colliding stars and the physics of their interiors, which remain a mystery. The rarity of these events makes them difficult to study, but each detection provides invaluable insights. By observing the light, gravitational waves, and ejected material from neutron star collisions, scientists can piece together the story of how these extreme objects behave and what they reveal about the universe. These collisions are not just cosmic spectacles, they are key to understanding the origins of heavy elements, the nature of gravity, and the life cycles of neutron stars. As we continue to explore the mysteries of neutron star collisions, we're reminded of the universe's ability to create beauty and chaos in equal measure. These events are a testament to the incredible forces at work in the cosmos, and they challenge us to keep pushing the boundaries of our knowledge. Next, we'll delve into another enigma, the mysterious interiors of neutron stars, where matter exists in states so extreme they defy our understanding. What lies beneath the surface of these cosmic powerhouses? Let's find out. Now, let's turn our attention inward, deep into the heart of neutron stars, where the mysteries only grow more profound. Beneath their solid, ultra-dense crust lies a realm of matter so extreme that it defies everything we know about physics. Here, the pressures are so immense that atoms are crushed into a bizarre soup of subatomic particles, creating states of matter that can't exist anywhere else in the universe. At the core of a neutron star, scientists believe matter may exist in forms like quark-gluon plasma, a state where protons and neutrons break down into their most basic components, quarks and gluons. This exotic material is thought to be similar to what existed just moments after the Big Bang, offering a rare glimpse into the universe's earliest moments. But studying it is no easy task. The conditions inside a neutron star are so extreme that they can't be replicated in any laboratory on Earth. Instead, scientists rely on theoretical models and observations to piece together what might be happening in these cosmic pressure cookers. One of the biggest challenges is understanding how matter behaves under such crushing densities. At the core, the pressure is so intense that it might even force quarks to rearrange themselves into entirely new configurations, forming what's known as strange matter. This hypothetical state of matter could be more stable than anything we've ever encountered, but it remains purely theoretical for now. To test these ideas, researchers use powerful supercomputers to simulate the conditions inside neutron stars, running complex calculations that take into account the laws of quantum mechanics and general relativity. These simulations help scientists predict how matter might behave, but they also raise new questions about the limits of our understanding. Another puzzle is the role of superfluidity, a state where matter flows without any friction. In the outer layers of a neutron star, scientists believe that neutrons may form a superfluid, allowing them to move freely and potentially explaining phenomena like pulsar glitches. But deeper inside, the behavior of matter becomes even more uncertain. Could there be layers of superfluid quarks or other exotic particles? The answers remain hidden, waiting to be uncovered. Despite the challenges, every new observation brings us closer to unraveling these mysteries. By studying the gravitational waves emitted during neutron star collisions or analyzing the light from pulsars, scientists can gather clues about what lies beneath the surface. These observations, combined with cutting-edge simulations, are slowly painting a picture of neutron star interiors. A picture that challenges our understanding of matter, energy, and the very fabric of the universe. As we peer into the depths of these cosmic enigmas, we're reminded of how much we still have to learn. The interiors of neutron stars are a frontier of physics, where the known rules of the universe are pushed to their limits. And while the answers remain elusive, the journey to uncover them is as thrilling as the mysteries themselves. Next, we'll explore another fascinating aspect of neutron stars, how they cool over time, and why some seem to lose heat faster than expected. What secrets do their cooling rates hold? Let's dive in. Now, let's shift our focus to another intriguing mystery, how neutron stars cool over time, and why some seem to lose heat at a surprisingly rapid pace. Neutron stars are born scorching hot, with temperatures reaching hundreds of billions of degrees, but they don't stay that way forever. over millions of years, they gradually cooled down, and the way this happens holds clues to their inner workings and the exotic physics at play. One of the key players in this cooling process is the neutrino, a ghostly, nearly massless particle that rarely interacts with matter. Neutrinos are produced in enormous quantities inside neutron stars, especially in their ultra-dense cores. These particles carry away energy as they escape, acting like a cosmic cooling system. But here's the twist: not all neutron stars cool at the same rate. Some appear to lose heat much faster than expected, and scientists are still trying to figure out why. One leading theory involves the presence of exotic particles or states of matter in the neutron star's core. For instance, if quarks are free to move around in a quark-gluon plasma, they might produce more neutrinos, accelerating the cooling process. Alternatively, the core might contain particles like pions or kaons, which could also enhance neutrino production. These exotic particles could explain why some neutron stars cool faster than others, but detecting them directly is nearly impossible with current technology. Another factor that complicates the picture is the neutron star's magnetic field. Strong magnetic fields can influence how heat is transported from the core to the surface, potentially affecting the cooling rate. Some neutron stars, like magnetars, have magnetic fields trillions of times stronger than Earth's, and these fields might play a role in how quickly they lose heat. However, the exact mechanisms remain unclear, and researchers are still working to untangle the relationship between magnetic fields and cooling. Observations of neutron stars at different stages of their lives provide valuable insight. Younger neutron stars, still glowing from their supernova births, tend to cool rapidly at first, but the rate slows down as they age. However, some older neutron stars seem to defy expectations, cooling faster than models predict. This discrepancy suggests that there's more to the story than we currently understand, and it's driving scientists to refine their theories and simulations. By studying the light emitted by neutron stars across different wavelengths, from X-rays to radio waves, astronomers can estimate their temperatures and cooling rates. These observations, combined with advanced computer models, are helping to piece together the puzzle. But every new discovery seems to raise more questions, reminding us just how complex these cosmic objects are. The mystery of neutron star cooling isn't just about understanding how they lose heat, it's about uncovering the secrets of their interiors and the exotic physics that govern them. As we continue to observe and study these stellar remnants, we're not only learning about neutron stars but also gaining insights into the fundamental nature of matter itself. Next, we'll explore another layer of these cosmic enigmas, the thin, mysterious atmospheres that surround neutron stars and how they influence the radiation we detect from them. What can these atmospheres tell us about the stars beneath them? Let's find out. Now, let's turn our attention to the thin, mysterious atmospheres that cloak neutron stars. These atmospheres, though incredibly thin compared to Earth's, play a crucial role in shaping the radiation we detect from these cosmic objects, but studying them is no easy task. Neutron star atmospheres are so faint and complex that they've remained one of the most challenging aspects of neutron star research. The atmosphere of a neutron star is a thin layer of gas, often just a few centimeters thick, sitting above the star's solid surface. This layer is made up of elements like hydrogen, helium, or even heavier elements like carbon or oxygen, depending on the star's history and environment. But here's the catch: the extreme gravity of a neutron star, billions of times stronger than Earth's, compresses this atmosphere into a dense, hot layer that behaves in ways we're still trying to understand. One of the biggest challenges in studying these atmospheres is their sheer distance from us. Neutron stars are incredibly far away, and their atmospheres are so faint that even the most advanced telescopes struggle to capture detailed observations. To make matters more complicated, the radiation emitted by neutron stars passes through these atmospheres before reaching us, and the atmosphere can alter the light in subtle but significant ways. This means that to truly understand the radiation we detect, we need to decode the influence of the atmosphere first. The composition and temperature of the atmosphere can dramatically affect the type of radiation emitted. For example, if the atmosphere is rich in hydrogen, it might produce a specific pattern of X-rays that differs from a helium-rich atmosphere. These differences help astronomers infer the atmosphere's composition, but the process is far from straightforward. The extreme conditions on neutron stars, intense magnetic fields, high temperatures, and crushing gravity, make the physics of these atmospheres incredibly complex. Even small changes in the atmosphere's properties can lead to big changes in the radiation we observe. Another layer of mystery comes from the interaction between the atmosphere and the neutron star's magnetic field. In some cases, the magnetic field can trap particles in the atmosphere, creating hotspots that emit intense bursts of radiation. These hotspots can make the star appear brighter in certain areas, adding another layer of complexity to our observations. Understanding how these magnetic fields shape the atmosphere is key to unraveling the true nature of neutron star emissions. Despite these challenges, scientists have made significant progress. By analyzing the light from neutron stars across different wavelengths, from X-rays to visible light, they've been able to piece together some of the properties of these atmospheres. Advanced computer models also help simulate the extreme conditions, providing insights that observations alone can't reveal. But every discovery seems to open up new questions, reminding us just how much we still have to learn. The mystery of neutron star atmospheres isn't just about understanding a thin layer of gas, it's about decoding the signals these stars send us and uncovering the secrets of their inner workings. As we continue to study these elusive layers, we're not only learning about neutron stars but also gaining a deeper understanding of the universe's most extreme environments. Next, we'll dive into another fascinating phenomenon, starquakes on neutron stars, and how these cosmic tremors release unimaginable amounts of energy. What causes these quakes and what can they tell us about the stars themselves? Let's explore. Now, let's shift our focus to one of the most dramatic events in the life of a neutron star, starquakes. Imagine a cosmic tremor so powerful that it releases more energy in a fraction of a second than our Sun does in thousands of years. These starquakes, also known as glitches, are sudden shifts in the crust of a neutron star, and they offer a fascinating glimpse into the inner workings of these dense, mysterious objects. Neutron stars are not perfectly smooth spheres. Their surfaces are made up of a solid crust, just a few kilometers thick, floating atop a superfluid core. This crust is incredibly dense and rigid, but it's not indestructible. Over time, the intense magnetic fields and rapid rotation of the neutron star can cause stress to build up in the crust. When that stress becomes too much, the crust cracks, releasing a massive amount of energy in the form of a starquake. Detecting these quakes is no small feat. Scientists rely on the pulses of radiation emitted by neutron stars, particularly pulsars, to spot these events. When a starquake occurs, it can cause a sudden change in the star's rotation speed, known as a glitch. This change is picked up by telescopes as a slight shift in the timing of the pulsar's pulses. In some cases, the quake can also produce a burst of gamma rays or X-rays, which can be detected by space-based observatories. But what exactly causes these quakes? One leading theory involves the interaction between the neutron star's crust and its superfluid interior. The core of a neutron star is thought to be a superfluid, a state of matter that flows without friction. As the star rotates, the superfluid core can spin faster than the crust. Over time, this difference in rotation can create tension in the crust, eventually causing it to crack. Another possibility is that the intense magnetic fields of magnetars, neutron stars with extremely strong magnetic fields, can twist the crust, leading to fractures. The energy released during a starquake is staggering. In just a fraction of a second, a single quake can release as much energy as a magnitude 23 earthquake on Earth. To put that in perspective, the most powerful earthquake ever recorded on Earth was around magnitude 9.5. These quakes not only reshape the surface of the neutron star, but also provide scientists with valuable clues about the star's internal structure and composition. Studying starquakes helps us understand the extreme conditions inside neutron stars. By analyzing the changes in rotation and the bursts of radiation they produce, scientists can infer details about the crust's thickness, the strength of the magnetic fields, and even the properties of the superfluid core. Each quake is like a cosmic experiment, revealing new insights into the physics of these enigmatic objects. As we continue to observe and study neutron star quakes, we're reminded of just how dynamic and unpredictable these cosmic objects can be. They're not just static remnants of supernova, they're living, evolving entities, constantly reshaping themselves under the influence of unimaginable forces. Next, we'll explore another intriguing aspect of neutron stars, their magnetic fields, and why some stars have fields trillions of times stronger than Earth's. What creates these magnetic powerhouses, and how do they shape the life of a neutron star? Let's find out. Now, let's turn our attention to one of the most awe-inspiring features of neutron stars, their magnetic fields. These fields are not just strong, they are among the most powerful forces in the universe. To put it into perspective, the magnetic field of a typical neutron star can be trillions of times stronger than Earth. But what creates these magnetic powerhouses, and why do some neutron stars have fields that dwarf others? The answers lie in the chaotic and extreme conditions of their birth. When a massive star collapses into a neutron star, its magnetic field doesn't just disappear, it gets compressed and amplified. Imagine taking a bar magnet and squeezing it down to the size of a city. The magnetic field becomes incredibly concentrated, resulting in the intense fields we observe. But not all neutron stars are created equal. Some, known as magnetars, have magnetic fields that are 1,000 times stronger than those of regular neutron stars. These magnetars are so powerful that their fields can distort the shape of atoms and even affect space-time itself. So, what makes magnetars so special? One theory suggests that their extreme fields are the result of a process called dynamo action. During the supernova explosion that forms a neutron star, the core of the collapsing star spins rapidly, and its magnetic field gets twisted and amplified. If the star is spinning fast enough, this dynamo effect can create a magnetar. Another possibility is that magnetars are born from the merger of two neutron stars, an event so violent that it generates an ultra-strong magnetic field. But why do some neutron stars have weaker fields? It turns out that the strength of a neutron star's magnetic field can change over time. As a neutron star ages, its magnetic field may slowly decay. This decay happens because the intense heat and pressure inside the star cause the magnetic field to dissipate over millions of years. Some neutron stars, particularly those in binary systems, may also have their fields weakened by interactions with their companion stars. These interactions can strip away the outer layers of the neutron star, reducing its magnetic field in the process. The behavior of neutron star magnetic fields is also influenced by their rotation. As a neutron star spins, its magnetic field generates powerful electromagnetic radiation, which can slow down the star's rotation over time. This process, known as magnetic braking, is why older neutron stars tend to spin more slowly and have weaker magnetic fields. However, in some cases, the magnetic field can also cause the star to spin faster, especially if it's interacting with material from a nearby companion star. Studying neutron star magnetic fields is not just about understanding these cosmic objects, it's also about unlocking the secrets of the universe. These fields play a crucial role in shaping the environment around neutron stars, from powering the beams of radiation in pulsars to triggering the explosive bursts of magnetars. They also provide a unique laboratory for testing the laws of physics under extreme conditions, offering insights into everything from quantum mechanics to general relativity. As we continue to explore the mysteries of neutron star magnetic fields, we're reminded of the incredible diversity and complexity of these cosmic objects. From the ultra-strong fields of magnetars to the fading fields of older neutron stars, each one tells a unique story about the life and death of stars. Next, we'll dive into another fascinating aspect of neutron stars, their spin rates. Why do some neutron stars spin hundreds of times per second, while others rotate much more slowly? Let's unravel this cosmic puzzle together. Now, let's shift our focus to another fascinating aspect of neutron stars, their spin rates. Why do some neutron stars spin hundreds of times per second, while others rotate at a much more leisurely pace? The answer lies in a combination of their origins, their environments, and the forces acting upon them. When a neutron star is born from the collapse of a massive star, it inherits the angular momentum of its progenitor. Think of it like a figure skater pulling in their arms during a spin. The star's core collapses, causing it to spin faster. This initial spin can be incredibly rapid, with some newborn neutron stars rotating hundreds of times per second. These fast-spinning neutron stars are often observed as pulsars, their beams of radiation sweeping across space like cosmic lighthouses. But not all neutron stars maintain these blistering speeds. Over time, their spin rates can change due to a process called magnetic braking. As a neutron star's magnetic field interacts with its surroundings, it emits energy in the form of electromagnetic radiation. This energy loss gradually slows the star's rotation, causing older neutron stars to spin more slowly. In some cases, this slowdown can take millions of years, turning what was once a rapid spinner into a more sedate cosmic object. However, the story doesn't end there. Some neutron stars defy this trend and actually speed up. This happens when a neutron star is part of a binary system orbiting a companion star. If the companion star transfers material onto the neutron star, the infalling matter can carry angular momentum, effectively revving up the neutron star's spin. These systems, known as accretion-powered pulsars, can spin hundreds of times per second, rivaling the speeds of the youngest neutron stars. Another factor influencing spin rates is the neutron star's internal structure. The interior of a neutron star is thought to contain superfluid neutrons which can flow without friction. When the crust of the neutron star slows down due to magnetic braking, the superfluid interior may resist this change, leading to sudden increases in spin rate known as glitches. These glitches provide a glimpse into the complex dynamics at play within neutron stars, revealing how their interiors interact with their surfaces. The diversity in neutron star spin rates also raises intriguing questions about their evolution. Why do some neutron stars slow down more quickly than others? Why do some remain fast spinning even after billions of years? These questions are still being explored, with astronomers using advanced telescopes and gravitational wave detectors to study neutron stars in unprecedented detail. Understanding neutron star spin rates isn't just about solving a cosmic puzzle, it's about piecing together the life stories of these extraordinary objects. From their explosive births to their interactions with companion stars, each neutron star's spin rate tells a unique tale of its journey through the cosmos. Next, we'll explore another captivating mystery: the companions that orbit neutron stars. What kinds of objects can share their cosmic dance, and how do these partnerships shape their evolution? Let's find out. Now, let's turn our attention to the cosmic companions that share their journey with neutron stars. These stellar remnants don't always travel alone. Many are found in the company of other celestial objects, from planets to stars, creating some of the most intriguing systems in the universe. The types of companions a neutron star has can dramatically influence its behavior and evolution, making these partnerships a key piece of the neutron star puzzle. One of the most fascinating companions a neutron star can have is another star. In binary systems where a neutron star orbits a companion star, the interaction between the two can lead to extraordinary phenomena. For instance, if the companion star is a massive, aging star, it may transfer material onto the neutron star. This process, known as accretion, can power intense X-ray emissions and even cause the neutron star to spin faster, as we discussed earlier. These systems, called X-ray binaries, are cosmic laboratories that allow us to study the effects of mass transfer and the extreme physics at play. But neutron stars don't always pair with massive stars. Some have companions that are much smaller, like white dwarfs or even other neutron stars. When two neutron stars orbit each other, they create a system that's ripe for dramatic events. Over time, their orbits can decay due to the emission of gravitational waves, eventually leading to a collision. These collisions are not only spectacular to witness, but also play a crucial role in the universe, producing heavy elements like gold and platinum, and sending ripples through space-time that we can detect with gravitational wave observatories. Interestingly, neutron stars can also have planets as companions. These planets, often called pulsar planets, are some of the most exotic worlds in the cosmos. They form in the aftermath of a supernova, either from the debris left behind or from material captured later. One of the first exoplanets ever discovered actually orbits a pulsar, proving that even in the chaotic environment of a neutron star, planets can find a way to exist. However, life on these planets would face extreme challenges, from intense radiation to gravitational forces that could tear worlds apart. The formation of these companion systems is as varied as the companions themselves. In some cases, the neutron star and its companion form together from the same stellar nursery, bound by gravity from the start. In others, the neutron star captures a companion later in its life, either through gravitational interactions or by pulling material from a passing star. Each scenario leaves its mark on the system, influencing how the neutron star and its companion evolve over time. As we study these systems, we uncover not just the secrets of neutron stars, but also the broader story of how celestial objects interact and shape the universe. The companions of neutron stars are more than just cosmic neighbors, they're partners in a dance that reveals the intricate connections between stars, planets, and the forces that govern them. Next, we'll dive into another captivating mystery, the powerful jets of particles that some neutron stars emit. What drives these jets, and what can they tell us about the inner workings of these cosmic powerhouses? Let's explore. Now, let's shift our gaze to one of the most visually stunning phenomena in the cosmos, the powerful jets of particles that some neutron stars unleash into space. These jets are not just cosmic fireworks, they are intense streams of energy and matter that stretch across vast distances, sometimes even spanning light years. But what exactly powers these jets, and why are they so incredibly energetic? Let's unravel this mystery. Neutron star jets are born from the extreme environment surrounding these dense stellar remnants. When a neutron star is part of a binary system, it often pulls material from its companion star. As this material spirals toward the neutron star, it forms a swirling disk of gas and dust called an accretion disk. The intense gravitational and magnetic forces at play heat this disk to incredible temperatures, causing it to emit radiation across the electromagnetic spectrum, from radio waves to X-rays. But that's not all. Some of this material doesn't fall onto the neutron star. Instead, it gets funneled along the neutron star's magnetic field lines and blasted outward at nearly the speed of light, forming the jets we observe. What makes these jets so energetic? The answer lies in the neutron star's immense gravity and its incredibly strong magnetic field. As material accelerates along the magnetic field lines, it gains tremendous energy, much like a slingshot flinging a stone at high speed. The result is a beam of particles so powerful that it can outshine entire galaxies in certain wavelengths. These jets are not just fast, they are also incredibly focused, often appearing as narrow beams that extend far into space. This precision is what makes them so striking when observed through telescopes, but the mystery doesn't end there. Scientists are still trying to understand why some neutron stars produce jets while others don't. One theory suggests that the strength and orientation of the neutron star's magnetic field play a crucial role. If the magnetic field is aligned in just the right way, it can channel material into jets more efficiently. Another factor could be the rate at which material is being pulled from the companion star. Too much or too little accretion might disrupt the formation of jets, adding another layer of complexity to this cosmic puzzle. These jets are more than just spectacular displays, they also serve as cosmic probes, helping us understand the extreme physics at work near neutron stars. By studying the properties of these jets, such as their speed, structure, and energy output, scientists can learn more about the neutron star's magnetic field, its rotation, and even the nature of the material being ejected. In a way, these jets are like cosmic messengers, carrying information about the inner workings of neutron stars across the universe. As we continue to explore the mysteries of neutron star jets, we're reminded of just how dynamic and interconnected the cosmos truly is. These jets are not just isolated phenomena, they are part of a larger story of how neutron stars interact with their surroundings and shape the universe around them. Next, we'll turn our attention to another intriguing aspect of neutron stars: how scientists determine their ages and why some appear to defy the expected timeline. Stay tuned as we uncover more secrets of these cosmic enigmas. Now, let's turn our attention to a question that has puzzled astronomers for decades. How old are neutron stars, and why do some seem to defy the expected timeline? Determining the age of these cosmic remnants is no simple task, and the answers often lead to more questions than clarity. So, how do scientists even begin to estimate the age of something as enigmatic as a neutron star? One of the primary methods involves studying the neutron star's spin. When a neutron star is born from a supernova, it spins incredibly fast, sometimes hundreds of times per second. Over time, this spin slows down as the star loses energy through radiation and particle emissions. By measuring how quickly a neutron star is slowing down, scientists can estimate its age. This method, known as the spin-down age, provides a rough timeline, but it's not always precise. Factors like the star's magnetic field strength and the surrounding environment can influence its spin rate, making some neutron stars appear older or younger than they really are. Another clue comes from the remnants of the supernova explosion that created the neutron star. By studying the expansion rate of the supernova remnant and comparing it to the neutron star's current position, astronomers can estimate how long ago the explosion occurred. However, this method has its limitations too. Some neutron stars are found far from their birthplaces, having been kicked away by the force of the supernova explosion or through interactions with other objects in space. This makes it difficult to trace their origins and determine their true age, but here's where things get even more intriguing. Some neutron stars appear to be much older or younger than expected based on these methods. For instance, certain neutron stars in binary systems seem to have ages that don't match their companions. This discrepancy has led scientists to consider other factors, such as the possibility of neutron stars being rejuvenated by interactions with their companion stars. In these cases, the neutron star might gain material from its companion, which could alter its spin rate and make it appear younger than it actually is. On the other hand, some neutron stars appear to be older than the universe itself, a clear impossibility. This paradox arises from the limitations of our current methods and the complex physics at play. For example, neutron stars with unusually strong magnetic fields might slow down faster than expected, making them seem older. Alternatively, some neutron stars might have formed through processes we don't yet fully understand, such as the merger of two white dwarfs, which could complicate age estimates. The mystery of neutron star ages reminds us just how much we still have to learn about these cosmic objects. Each discovery brings new insights but also new questions. As we continue to refine our methods and explore the universe with ever more advanced tools, we may one day unlock the secrets of how and when neutron stars are born, and why some seem to exist outside the bounds of time itself. Next, we'll explore another fascinating aspect of neutron stars, the upper and lower limits of their mass, and why these boundaries remain one of the greatest puzzles in astrophysics. Stay with us as we dive deeper into the mysteries of the cosmos. Now, let's shift our focus to one of the most fundamental questions about neutron stars: how massive can they actually be? The mystery of neutron star mass limits is a puzzle that challenges our understanding of physics at its most extreme. Neutron stars are incredibly dense, packing more mass than our Sun into a sphere no wider than a city. But just how much mass can they hold before collapsing under their own gravity? And what happens if they're too light? These questions lie at the heart of one of astrophysics' greatest enigmas. To understand the upper mass limit of neutron stars, we need to consider the delicate balance between gravity and the forces that hold matter together. When a neutron star forms, gravity crushes the core of a massive star into an incredibly dense state. But this crushing force is counteracted by something called neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed any further. Think of it like trying to compress a spring. There's a point where it simply can't be pushed anymore. For neutron stars, this balance determines their maximum mass. If a neutron star gains too much mass, say by pulling material from a companion star, it can tip the scales, causing the star to collapse into a black hole. Scientists estimate this upper limit to be around 2 to 3 times the mass of our Sun, but the exact number remains uncertain. On the other end of the spectrum, there's the lower mass limit. How small can a neutron star be? This question is just as intriguing. If a neutron star doesn't have enough mass, it might not be able to sustain the extreme conditions needed to form in the first place. Instead, it could collapse into a less dense object like a white dwarf. The lower limit is thought to be around 1/10 the mass of the Sun, but again, this is a rough estimate. The challenge lies in the fact that neutron stars are born from supernova, and the conditions during these explosions can vary widely, making it difficult to pin down precise numbers. What makes these limits so hard to determine? The answer lies in the strange and complex world of quantum mechanics. At the core of a neutron star, matter is compressed to such an extreme degree that it behaves in ways we can't fully predict. The neutrons themselves might break down into even smaller particles like quarks, creating a state of matter known as quark-gluon plasma. This exotic material could change the rules of the game, altering the balance between gravity and pressure in ways we don't yet understand. Additionally, the strong nuclear force, the force that holds atomic nuclei together, plays a critical role in stabilizing neutron stars. But this force is incredibly difficult to model under such extreme conditions, leaving scientists with more questions than answers. The mystery of neutron star mass limits isn't just a theoretical curiosity. It has real implications for our understanding of the universe. By studying these limits, scientists can learn more about the nature of matter itself, as well as the processes that govern the birth and death of stars. It also helps us understand the boundary between neutron stars and black holes, two of the most extreme objects in the cosmos. As we continue to explore this frontier, each discovery brings us closer to unraveling the secrets of these cosmic enigmas. Next, we'll delve into another fascinating phenomenon, the echoes of radiation that bounce off neutron stars, revealing clues about their surroundings and the mysteries they hold. Stay with us as we uncover more about these incredible objects. Now, let's turn our attention to a phenomenon that sounds almost like something out of science fiction: neutron star echoes. Imagine a beam of radiation shooting out from a neutron star, only to bounce off nearby material and return like a cosmic boomerang. These echoes are not just fascinating, they're a window into the environment surrounding these dense stellar remnants. But how do we detect them, and what secrets do they hold? Neutron star echoes occur when the intense radiation emitted by a neutron star interacts with the material in its vicinity. This could be gas, dust, or even the remnants of a supernova explosion. When the radiation hits this material, it scatters and reflects, creating a kind of echo that astronomers can detect. These echoes are incredibly faint, but with advanced telescopes and sensitive instruments, scientists have been able to pick up on these subtle signals. It's like listening for a whisper in a crowded room, challenging but not impossible. So, what do these echoes tell us? For one, they reveal the composition and structure of the material surrounding the neutron star. By analyzing the way the radiation is scattered, scientists can determine what kinds of elements are present and how they're distributed. This is crucial for understanding the aftermath of supernova and the environments in which neutron stars form. Echoes can also provide clues about the neutron star itself, such as its magnetic field strength and rotation rate. In some cases, they've even helped identify previously unknown neutron stars hidden behind thick clouds of dust. But detecting these echoes is no easy task. The signals are often buried in a sea of other cosmic noise, requiring sophisticated techniques to isolate and interpret them. One method involves studying the timing and energy of the radiation. Since neutron stars emit radiation in pulses, any echoes will arrive slightly later and with a different energy signature. By carefully analyzing these differences, astronomers can piece together the path the radiation took and the obstacles it encountered along the way. The mystery of neutron star echoes doesn't stop there. Some echoes have revealed unexpected structures, like rings or arcs of material around neutron stars. These features suggest that the environments around these objects are far more complex than we once thought. They could be remnants of the star's explosive birth, or they might be the result of interactions with a companion star or interstellar medium. Either way, each echo brings us closer to understanding the life and death of these cosmic powerhouses. As we continue to explore this phenomenon, neutron star echoes promise to unlock even more secrets about the universe. They remind us that even the faintest signals can carry profound insights waiting to be discovered. Next, we'll dive into another intriguing mystery, the possibility that neutron stars could be hiding dark matter in their cores. What could this mean for our understanding of the cosmos? Stay tuned as we uncover more about these enigmatic objects. Now, let's venture into one of the most intriguing possibilities in astrophysics, the mystery of neutron star dark matter. Could these incredibly dense stellar remnants be hiding dark matter within their cores? This idea isn't just a wild speculation, it's a hypothesis that could reshape our understanding of the universe itself. Dark matter, as you may know, is the invisible substance that makes up about 85% of the matter in the universe. It doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. Yet, its presence is felt through its gravitational effects on galaxies and galaxy clusters. So, how could neutron stars, some of the densest objects in the cosmos, be connected to this elusive material? One theory suggests that dark matter particles could accumulate in the cores of neutron stars over time. Because neutron stars are so dense, their immense gravitational pull might trap dark matter particles, causing them to gather in the star's center. Over billions of years, this accumulation could lead to a significant concentration of dark matter within the neutron star. But what would that mean for the star itself? Scientists speculate that the presence of dark matter in a neutron star's core could alter its properties in subtle but detectable ways. For instance, it might affect the star's cooling rate or even its stability. If dark matter particles interact with each other or with ordinary matter in the core, they could release energy, potentially slowing down the star's cooling process. This could explain why some neutron stars appear to cool more slowly than expected, but the implications go even further. If neutron stars do harbor dark matter, they could serve as natural laboratories for studying this mysterious substance. By observing how neutron stars behave, scientists might gain clues about the nature of dark matter particles, whether they're heavy or light, how they interact, and what role they play in the cosmos. This could bring us closer to solving one of the biggest mysteries in modern physics. Of course, detecting dark matter in neutron stars is no simple task. It would require precise measurements of neutron star properties, such as their mass, radius, and cooling rates, combined with advanced theoretical models. Some researchers are even exploring whether gravitational waves from neutron star collisions could reveal traces of dark matter in their signals. While the evidence is still speculative, the idea is tantalizing. The mystery of neutron star dark matter challenges us to think beyond what we know and explore the unknown. If proven true, it could not only explain some of the strange behaviors of neutron stars, but also provide a groundbreaking window into the nature of dark matter itself. As we continue to probe the depths of these cosmic enigmas, who knows what other secrets we might uncover? Next, we'll explore the full life cycle of neutron stars, from their explosive births to their eventual fates. What happens to these stellar remnants over billions of years? Let's find out. Now, let's turn our attention to the fascinating journey of neutron stars over cosmic timescales, the mystery of their life cycles. From their explosive beginnings to their eventual fates, neutron stars undergo dramatic transformations that span billions of years, offering a glimpse into the long-term evolution of some of the universe's most extreme objects. It all begins with the death of a massive star. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. This cataclysmic event leaves behind a neutron star, a dense remnant packed with the mass of a star but squeezed into a sphere only about 12 miles across. This is the birth of a neutron star, a moment of cosmic violence that sets the stage for its long and complex life cycle. In the early stages of their existence, neutron stars are incredibly active. They spin rapidly, sometimes hundreds of times per second, and emit powerful beams of radiation that we detect as pulsars. Over time, however, these young neutron stars begin to slow down. Their intense magnetic fields, which drive their energetic emissions, gradually weaken, and their spin rates decrease. This phase can last for tens of thousands to millions of years, depending on the star's initial conditions. As neutron stars age, they enter a quieter phase. Without the energy output of their younger counterparts, they become harder to detect. Some may fade into obscurity, while others continue to emit faint X-rays or other forms of radiation. During this time, neutron stars may also interact with their surroundings, accreting material from nearby stars or interstellar gas. These interactions can reignite their emissions, creating X-ray binaries or other exotic systems. But what happens to neutron stars over billions of years? One possibility is that they continue to cool and fade, eventually becoming cold, dark remnants known as black dwarfs. However, neutron stars are so dense and stable that this process could take far longer than the current age of the universe. Another intriguing possibility is that some neutron stars may collide with other neutron stars or black holes, producing gravitational waves and heavy elements like gold and platinum. These collisions are rare but have profound implications for the cosmos. The ultimate fate of a neutron star depends on its environment and interactions. In dense regions like globular clusters, neutron stars are more likely to encounter other objects, potentially leading to mergers or other dramatic events. In quieter regions of space, they may simply continue to cool and fade, becoming relics of a bygone stellar era. the life cycle of neutron stars is a testament to the dynamic and ever-changing nature of the universe. From their explosive births to their slow, quiet decay, these stellar remnants offer a window into the long-term processes that shape the cosmos. As we continue to study neutron stars, we uncover not only their secrets but also clues about the broader evolution of the universe itself. Next, we'll explore an even more intriguing question. Could life exist near these extreme objects? Let's dive into the mystery of neutron star habitability. Now, let's venture into one of the most speculative and fascinating mysteries of neutron stars, the possibility of life existing near these extreme cosmic objects. Could any form of life, no matter how resilient, survive in the harsh environment surrounding a neutron star? The answer lies in understanding the extreme conditions these stellar remnants create. Neutron stars are among the most hostile environments in the universe. Their surfaces are scorching hot, with temperatures reaching millions of degrees, and their gravitational fields are so intense that they can distort space and time. Add to that the powerful magnetic fields, which are trillions of times stronger than Earth's, and the constant bombardment of high-energy radiation, and it's clear why neutron stars seem like the last place life could thrive. But let's consider the possibilities. Life as we know it requires certain conditions: liquid water, a stable energy source, and protection from harmful radiation. Near a neutron star, these conditions seem impossible. However, some scientists have speculated about exotic forms of life that could adapt to such extremes. For example, life might exist on a planet orbiting a neutron star, shielded by a thick atmosphere or deep underground. Alternatively, life could take forms we can't yet imagine, relying on entirely different chemistry or energy sources. One intriguing scenario involves planets in the habitable zone of a neutron star. While these stars no longer produce light like a normal star, they emit X-rays and other forms of radiation that could, in theory, provide energy for life. If a planet were at just the right distance, it might receive enough energy to sustain liquid water, even if only in subsurface oceans. Such a planet would need to be incredibly resilient, with a strong magnetic field to protect it from the neutron star's radiation and gravitational forces. Another possibility is that life could exist in the debris disks surrounding neutron stars. These disks, formed from the remnants of the star's explosive birth, contain dust and gas that could potentially coalesce into planets or other structures. If life were to emerge in such a disk, it would have to withstand extreme temperatures and radiation. But the presence of organic molecules and water ice in these environments offers a glimmer of hope. Of course, these ideas remain highly speculative. The challenges of surviving near a neutron star are immense, and we have no direct evidence that life could exist in such conditions. Yet, the very idea pushes the boundaries of our understanding of life and its potential to adapt. It forces us to ask, what does it truly mean to be alive, and how far can life stretch to survive in the cosmos? As we ponder these questions, we're reminded of the incredible diversity and resilience of the universe. Neutron stars, with their extreme conditions, challenge our assumptions and inspire us to think beyond the familiar. Whether or not life exists near these cosmic enigmas, they remain a testament to the boundless possibilities of the universe. Next, we'll explore the broader significance of neutron stars and their role in shaping the cosmos. Now, let's shift our focus to the bigger picture and explore the profound role neutron stars play in the cosmos. These enigmatic objects are not just fascinating in their own right, they are cosmic powerhouses that shape the universe in ways we are only beginning to understand. One of their most significant contributions lies in the creation of heavy elements, the building blocks of planets, and even life itself. When neutron stars collide, they unleash unimaginable energy, producing gravitational waves that ripple through space-time. But that's not all. These collisions are also responsible for forging some of the heaviest elements in the universe, like gold, platinum, and uranium. This process, known as rapid neutron capture or the R process, occurs when free neutrons are absorbed by atomic nuclei at incredible speeds, creating elements far heavier than those formed in the cores of ordinary stars. Without neutron star collisions, many of the elements we rely on today simply wouldn't exist. But the influence of neutron stars extends far beyond element creation. They also play a crucial role in shaping galaxies. As they spin, neutron stars emit powerful beams of radiation and particles, which can heat up surrounding gas and dust, influencing the formation of new stars and planets. In some cases, neutron stars act as cosmic lighthouses, their beams sweeping across the galaxy and illuminating the interstellar medium, the vast clouds of gas and dust that fill the space between stars. Moreover, neutron stars are key players in the life cycle of galaxies. When they form in supernova explosions, they release enormous amounts of energy and matter into their surroundings, enriching the interstellar medium with heavy elements and triggering the birth of new stars. Over billions of years, this cycle of stellar death and rebirth helps galaxies evolve, grow, and diversify. Neutron stars also serve as natural laboratories for testing the laws of physics under extreme conditions. Their intense gravitational fields and magnetic forces allow scientists to study phenomena that can't be replicated on Earth, such as the behavior of matter at densities far beyond what we can imagine. By observing neutron stars, we gain insights into the fundamental forces that govern the universe, from gravity to quantum mechanics. In essence, neutron stars are more than just remnants of dead stars. They are cosmic architects, shaping the universe on both small and large scales. From creating the elements that make up our world to influencing the evolution of galaxies, their impact is truly universal. As we continue to study these extraordinary objects, we uncover not only their secrets but also the intricate connections that bind the cosmos together. Next, we'll look ahead to the future of neutron star research and the exciting discoveries that await us. Now, let's turn our gaze to the horizon and explore what the future holds for neutron star research. The mysteries of these cosmic enigmas are far from solved, but the tools and technologies on the horizon promise to unlock secrets we've only dreamed of uncovering. One of the most exciting advancements is the next generation of gravitational wave detectors. These instruments, like the planned upgrades to LIGO and the upcoming Einstein telescope, will allow us to detect even fainter ripples in space-time, giving us a clearer picture of neutron star collisions and the extreme physics at play. But gravitational waves are just the beginning. Advanced telescopes, both on the ground and in space, are set to revolutionize our understanding of neutron stars. For instance, the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, will peer into the hearts of neutron star remnants, revealing details about their formation and the elements they produce. Meanwhile, ground-based observatories like the Extremely Large Telescope will capture sharper images of neutron stars and their surroundings, helping us study their magnetic fields, atmospheres, and interactions with other cosmic objects. Another groundbreaking development is the rise of multi-messenger astronomy, which combines observations from different types of signals, like light, gravitational waves, and neutrinos, to paint a more complete picture of neutron stars. This approach has already yielded incredible insights, such as the detection of a neutron star collision in 2017 that was observed in both gravitational waves and light. As this field grows, we can expect even more discoveries that will deepen our understanding of these extreme objects. On the theoretical front, advancements in supercomputing are enabling scientists to simulate the extreme conditions inside neutron stars with unprecedented accuracy. These simulations help us explore the behavior of matter at densities so high that atoms collapse into a sea of neutrons, quarks, and other exotic particles. By comparing these models with real-world observations, researchers can test theories about the nature of matter and the fundamental forces that govern the universe. Looking further ahead, missions like the Laser Interferometer Space Antenna, or LISA, aim to detect gravitational waves from space, free from the interference of Earth's vibrations. This will open a new window into the universe, allowing us to observe neutron star mergers and other cosmic events with incredible precision. Similarly, proposed missions to study neutron stars up close, such as sending probes to measure their magnetic fields and surface properties, could provide direct insights into their structure and behavior. The future of neutron star research is brimming with potential, and each new discovery brings us closer to unraveling the mysteries of these cosmic powerhouses. As we continue to push the boundaries of technology and knowledge, we may soon find answers to questions that have puzzled scientists for decades. From the origins of heavy elements to the nature of matter itself, neutron stars hold the key to some of the universe's greatest secrets. And as we unlock them, we'll not only deepen our understanding of the cosmos, but also our place within it. Next, we'll explore how neutron stars have captured the imagination of humanity, inspiring art, culture, and our quest for knowledge. Now, let's shift our focus from the scientific to the cultural, and explore how neutron stars have sparked the imagination of not just scientists, but also artists, writers, and dreamers across the globe. These cosmic marvels, with their extreme nature and mysterious allure, have found their way into the fabric of our culture, inspiring stories, art, and even philosophical reflections on the universe. In the realm of movies and television, neutron stars have often been portrayed as the ultimate cosmic enigmas. Films like Interstellar and series like Star Trek have used neutron stars as backdrops for dramatic storytelling, showcasing their immense gravitational pull and the mind-bending physics they embody. These depictions, while sometimes exaggerated for dramatic effect, have brought the concept of neutron stars to a wider audience, sparking curiosity and wonder about these distant objects. Literature, too, has been deeply influenced by neutron stars. Science fiction authors like Arthur C. Clarke and Isaac Asimov have woven neutron stars into their narratives, using them as symbols of humanity's quest for knowledge and the limits of our understanding. In Clarke's The Neutron Tide, for instance, a neutron star becomes a metaphor for the relentless pull of time and destiny, while Asimov's works often explore the scientific and philosophical implications of these extreme objects. These stories not only entertain but also challenge readers to think deeply about the universe and our place within it. Artists have also been captivated by the beauty and mystery of neutron stars. From stunning visualizations of pulsar beams to abstract representations of their magnetic fields, neutron stars have inspired countless works of art. These creations often blend science and imagination, offering a unique perspective on the cosmos. For example, digital artists have used data from telescopes to create breathtaking images of neutron stars, transforming raw scientific information into visual masterpieces that resonate with both scientists and the public. Beyond their presence in media and art, neutron stars have also influenced our cultural understanding of the universe. They remind us of the vastness and complexity of space and the endless possibilities for discovery. They challenge us to think beyond our everyday experiences and consider the extraordinary forces that shape the cosmos. In this way, neutron stars are more than just scientific curiosities. They are symbols of humanity's enduring fascination with the unknown. As we reflect on the cultural impact of neutron stars, it's clear that their influence extends far beyond the realm of astrophysics. They have become a source of inspiration, a canvas for creativity, and a reminder of the boundless mysteries that await us in the universe. Next, we'll bring our journey to a close by summarizing the 25 mysteries of neutron stars and pulsars, and reflecting on what they mean for our understanding of the cosmos. As we wrap up our journey through the 25 mysteries of neutron stars and pulsars, it's clear that these cosmic wonders are far more than just remnants of stellar explosions. They are windows into the most extreme conditions in the universe, offering clues about the nature of matter, gravity, and even time itself. From their mind-bending density and mysterious interiors to their powerful beams and enigmatic glitches, neutron stars challenge our understanding of physics and push the boundaries of what we thought was possible. These celestial objects remind us that the universe is full of surprises and that every discovery raises new questions. Whether it's the missing pulsar in Supernova 1987A, the strange behavior of magnetars, or the potential connection to fast radio bursts, each mystery invites us to explore further and think deeper. Neutron stars are not just scientific curiosities, they are keys to unlocking the secrets of the cosmos. But the story doesn't end here. As technology advances and new missions like gravitational wave detectors and next-generation telescopes come online, we're poised to uncover even more about these fascinating objects. The mysteries of neutron stars and pulsars are a testament to the endless possibilities of discovery, and they inspire us to keep looking up and asking questions. So, what do you think about these cosmic enigmas? Which mystery fascinates you the most? Let us know in the comments below. We'd love to hear your thoughts. And if you enjoyed this deep dive into the mysteries of neutron stars and pulsars, don't forget to hit the like button, subscribe to our channel, and ring the notification bell so you never miss out on more cosmic adventures. The universe is full of wonders and we're just getting started. Thanks for watching, and until next time, keep exploring.